Good afternoon. Thank you for taking a few moments to sit here with us, and I will tell you that my Dutch is terrible, so you don't even ask me to try today. So, my name is Jim Satterwhite, and I'm actually from the U.S. We manufacture and engineer daylighting systems that are quite unique, and if we accomplish what we're looking for today, I think you'll understand a little bit about the technology. And to say that we are actually moving into European fabrication for this system now, and I hope you'll find it interesting as we go. We've entitled this presentation "Reinventing the Building Envelope" because there are some very confusing things that are happening systemically in the fenestration industry and broadly, and it's being driven by a number of things, and they're competing things that are revolving around getting proper daylight to human beings on the inside of the buildings, yet while practicing proper energy management. The two are really kind of at odds with each other. And what we've developed is a system and a series of systems which can provide some tools to work with that actually can solve some of the problems. So we're going to move through this fairly quickly because there's a lot of content here. Let me go back, okay. So when we think about glass for facades on buildings, this is what we think of. In that glass is kind of the quintessential design material to use for a high-performance building envelope, both from an aesthetic standpoint as well as from a quality standpoint into the space. Although glass also has difficulties associated with trying to use it as the entire envelope of a building. This particular example is a really good example of a building. This is the City Hall building in London, which was touted to be a model for daylighting in buildings around the world. But in actuality, it turned out to be a very problematic building from a daylighting perspective, and as we go through the rest of this presentation, we'll explain a little bit about why that is. But when you think about the design requirements to put a facade together, there's basically four essential elements that are in play at any time. One is actually the design language of the building. What is the desired image of the building? What's the desired rhythm of the exterior envelope of the building? Coupled with both what can we afford to spend on it and what are the energy requirements for it. All of those are in play. And also there's one not to be overlooked. Part of the reason that you're putting glass on a building is because you want views, you want daylight, you want the association with the indoor-outdoor migration. Getting used to all this technology. But let's talk a little bit about why the light is important. We have a relationship with visible light. The visible light spectrum affects us in a number of different ways. And the eye is actually a part of the brain. It's what actually communicates to the brain. It's directly connected. So there's an obvious association between the two medium. But we have two very different relationships to light that happen for us, both emotionally and physiologically. You've got, first off, what comes in through the eye communicates with the back of the brain, which gives us the emotional pleasure of having the indoor-outdoor connection. And it's that emotional benefit that you get from being able to see in and out. And it's what we need inside of buildings for them to provide or to perform functionally. But there's another component of it which is not necessarily thought of as directly, and that's that there's a direct physiological benefit to the exposure to the visible spectrum of light. And that is in a very specific wavelength, which is in the blue band, in the very far left band of the visible light spectrum that you see in the chart here, which doesn't solicit emotion. It solicits the physical response, the physiological response to the presence of daylight, and it triggers the pineal gland, which is responsible for secretion of melatonin and serotonins in our body. And it's literally what is caused for what everybody sees in terms of the benefits of daylighting, which are people learn better, people heal faster, workers produce more, and that's not necessarily purely an emotional response. It's really more of a physiological response because your bodies function better when you have the right association with the right spectrum of light inside of a building. And in reality, often we're doing daylighting because we're trying to save money on energy. It's a good thing to do, and it's a good thing to reduce carbon footprint and the carbon output, but it's also, from an economic standpoint, the cost associated with what goes on in the building and those responsible for functioning in the space is orders of magnitude more than the energy cost for the building ever would be in any year. So validating the benefits of daylighting is actually very easy to do as long as you quantify it all the way back to the end user of the building. But there's interesting problems in trying to actually engineering daylight. I like this image to say that the fallacy of daylighting because this shows the two in one shot, this shows the two possible means of accomplishing daylighting in space. And in today's genre, the majority of time people are thinking about daylighting as an all-glass facade, that you have to have an all-glass facade to actually bring proper daylight into a space. It's a drive for maximum visible light transmitting, maximum. But the reality is you can use either of these constructs done correctly and get a good daylit space. So you've got the punched opening in the reflection building, or you've got the all-glass facade in the other building. However, you have to think about managing and engineering the daylight correctly for the outcome to be correct. Where vision glass falls down is that it doesn't do anything to redirect light. It just lets light come in at whatever the incidence angle it is, and it does nothing to change the visible results in the space. Like back in here, you can see it's dark in this space. It's light only in this band here. And the result is you've got a very high contrast ratio between the bright areas and the dark areas, which you've got to mitigate. And typically the mitigation is, because of the contrast, glare is a problem, so window shades go up, reduces the amount of light transmission coming into the space, and lights go on because it's dark at the back of the room. But in reality, the issue is very well demonstrated here, which is, again, the user experience in the space. Here you've got a student sitting in a classroom. His work surface has way too much light on it. His eyes are in a dark space, so his pupils are actually dilating in that space, which makes the contrast ratio between the light and the dark even more painful. And if you multiply this by the numbers of students in the room that are all having a completely different experience, the typical solution for this is we put up this wonderful facade, but we drop blinds on it, we switch on the lights because we've got all this problem to deal with to make it useful. And in reality, it's really a symptom of dysfunctional design that doesn't take into consideration the total end user experience associated with daylighting the space. And in reality, when blinds go closed, they almost always stay closed. I go back to the City Hall building in London that I talked about. The building is a mishmash of open and closed blinds, very expensive because of that sloping curve facade. And the blinds are breaking all the time, and it's just a real problem. And this is the problem. So you're missing the physiological and emotional benefit of both the connection to the outdoors and the benefit of the daylighting, because you're going to close the blinds and they stay closed. So why do it? Why do it that way if there are options for not having to do it? From a design standpoint, there's an arsenal of options that designers have today, but they're always materials that block light, literally. So you put up an all-glass facade in these examples here, and you're bolting things onto the outside, or you're bolting things onto the inside, or you're putting mechanical shades up. In every case, they block light. So you're kind of going circuitously back to where you were trying to get away from in the first place. And this just requires forethought before you actually go there. But on a solution basis, what if we could actually use the glass to redirect light so that we get the full benefit of it? And incidentally, if it's really efficient at redirecting light, it eliminates the glare circumstance. So you can get the light, not have the glare, and get the benefits from the light by using a smart glass or a combination of very good optically redirecting light and vision glass so that you can get the two together. So if you had a perfect glass, it would redirect light something like you see here. And you see the difference in that space from this pattern to the next pattern, especially towards the back of the room. You've got an even cast of light coming through the space. Here's a couple of examples of how you can actually do this done in radiance modeling. These are actually real-life situations that were ultimately built, but these radiance options really give you the ability to see before and after in real time. So here's a case of a field house where the university wanted an all-glass facade because it was right at the entrance to the university, so they wanted that all-glass ambiance to it. But you can see by the image drawn on the left that field house had an all-glass facade. The amount of high contrast that you've got between light and dark, and a very dingy back portion of the room, this would be a disaster of a field house. And the only solution would be to drop blinds, turn on the lights. Using just a portion of that facade with light redirecting glass at the high bay, it changes the interior aspect completely, and it went from what was completely non-functional to something that's completely functional. And it's because when you have light redirecting glass, I think the right way to explain it is the type of light that comes from that is like a cloud of light. If you look at it that way, and if you have a direct beam that goes into a cloud, what do you end up with is diffused light. So what it does is it mitigates the high contrast between light and dark, which is the definition of glare. So you end up with something that could have been completely dysfunctional into something that's very functional. Do the same thing in a classroom environment. This is pretty classic in a learning environment. And we've mapped the foot candles on the desk surfaces for you here. And these foot candle readouts on the desks are completely too much light, way too much light. But more importantly, in the learning area where the teacher is standing, there's not enough light going on there. Plus, it's kind of a dark, dingy space. And what happens there is that the teacher who's in the dark area, pupils are dilating. All those students look like silhouettes out there. There's no interaction going on between them, and it's just completely dysfunctional space. So the usual solution is you drop blinds, flip on the lights, you get the story. But again, if you just use a component of that space that is using light redirecting, same day of the year, same time of day, the end result is completely different. You have a very nicely daylit space. You have an extremely reduced G value to the facade as well, and you've got a totally functionally daylit space. So in all cases, you're combining one functionality with the other to end up with a balanced end product. But it's important to understand that not all translucent materials are equal. You have to be able to actually measure the amount of light scatter to be able to map what's actually going to happen, and they all behave differently. So we've developed means of doing that. And here's a nice rendition that shows you a simple office space with various glazing options you have, with light coming in at a 45-degree angle, clear to acid etched. You see you've got way too much light on the surface of the desk. You can go to white laminated glass. You still have got no significant redirection of light. The Solera product that we're talking about that redirects light omnidirectionally, you end up with a very functional space here. So in every one of the previous examples there, you would have had to drop window blinds, flip on the lights to make the space functional. Now it's entirely functional as a glazed unit. So it's possible to work with a lot of glass and make it very functional. It's also possible to work with less glass, omnidirectionally transmitting light, and get better daylighting to the interior space and reduce the energy content both on a G value basis and also on an insulating value basis. So if it's possible, why are we even talking? Well, the reality of it is glass building envelopes are under attack these days. And they're under attack because of the poor performance of fenestration products, specifically glass. So using all glass is more and more difficult to use because of poor energy performance that's associated with them. These are two articles, one in the Sunday Times in London, another in the US in a major glass trade operation. But the reality is where things are going is the window to wall ratios are changing, and they're reducing the amount of window allowance to wall allowance to hit an overall performance for the building envelope that is making the use of glass harder and harder, which is, this goes against the pull for daylighting spaces and doing them well. And this is where using redirecting light can actually benefit. So the overall window wall ratio needs to be reduced according to all the model codes. And what ends up happening as a result of that is that the balance of all the things that the design community is trying to work with in terms of balancing the design, the affordability, energy performance, and the daylighting and views is actually being blown apart. So the whole genre of trying to practice proper daylighting in a fenestration environment is really suffering. And really the reason is that glass technology has hit its apex. And I think the easiest way to make this in a very short, sweet statement is that when you're thinking about insulating glass, you're thinking about putting together a group of materials that are extremely highly thermally conductive and expecting them to insulate. And where the industry resides now in terms of a best practice is a triple glazed unit with double OE and krypton gas, which is still kind of ho-hum relative to some other options that are available, but it's the best that the industry can use, and it performs at a very high level for a specific period of time. And it's not for lack of trying, it's just that the actual construct itself is limited to what it's actually able to do. And we think that the glass is at its apex because as soon as you start doing triple glass with double layers of low E, you also start ending up with some very unusual optical appearances to it that are very objectionable from an elevational standpoint, some leoparding and things like that go on that really start to play into the envelope aesthetics. So it's right at that end, right at that edge. So we think we have an answer to it. We use this in combination with those other materials. And this product is in its simplest form, it's an insulated glass unit that combines other attributes that give it tunable performance. So if you think about it, the construct, it's an IGU that uses a honeycomb material on the interior of it. And the honeycomb can be filled with aerogel and various thicknesses of aerogel to provide the thermal benefit that you're looking for. Then we use glass veils that are various densities of glass veils to do the light redirection, and it all goes together in an insulated glass assembly. You think about it just like any other insulated glass that you would use. It fits in a standard framing system, curtain wall system, and various configurations of it to meet different requirements. So what you end up with is this beautifully optically redirecting material that's very simple to use in standard systems, and provides incredible performance. So what makes it work? Well, from an insulation standpoint, it's the aerogel. From the light redirection standpoint, it's the light veils. And we have an infinite number of combinations that can be utilized and modeled virtually before the construct to make sure that they perform correctly. But to understand aerogel, if you haven't worked with aerogel or don't know aerogel, the thing with aerogel, if I can animate this, I don't know if it'll work. There we go. So just to put some perspective to it, aerogel is the most highly insulating material in the world. It also happens to be almost clear, almost water clear. And what makes it insulate so well is it's porous at a nanoscale, and it stops the two primary culprits that are in existence in a glass window for thermal transfer are gas phase conduction and convection, are the things that happen on the insulating space inside a glass. In order to eliminate the bulk of the problem, you have to eliminate the gas phase conduction. And the only way to do that is to have an insulating material whose pore structure is smaller than the distance between the air molecules. Because when the air gets in balance, the air molecules start moving around, as you see on your left here. And every time they touch each other, they grab energy from the other one. So they transfer the energy across the space through this atomic transfer of energy. What makes aerogel perform so fabulously is that the pore structure of the aerogel is smaller than the distance between the molecules. So just as you see up here, what's happening is it's stopping the ability for the molecules to come in contact with each other, so that you're ending up with a much lower degree of thermal transfer through the unit. You vary the thickness of these materials, you vary the total insulation performance, and you vary the G value by the various thicknesses of the material. So what you end up with there then is a family of materials, and it's quite a wide range you'll see here, from visible light transmittance from as low as a spandrel, it can be configured as a spandrel, to as high relative of 65% for any of the configurations of the material. In all cases, light distribution is tuned exactly the same way. So you can tell me that you want a U value of a unit, say our best at 0.23, and you want a visible light transmission of 20, but maybe on the north side you don't need all of that insulation, but you still want the 20% light transmission. We can do that through the entire range. So you can see here you've got solar transmission very widely ranged, and then you've got U values from as high as a 2.65 to as low as a 0.23. So wide palette of products. So use value where you get value. Don't use it where it's not delivering value. Sizes are 1.5 and 2 by 3.7 meters. And also the thicker units have a very interesting SDC capability of 54, which is very unusual in any building envelope material. That's being driven predominantly by the aerogel. The aerogel is very good at sound absorptions. And again, fits right into any standard framing system, be it storefront, be it window wall, be it curtain wall, all of the above. And so it's simple to use in structural glazing as well as in captured glazing. But let's take a visit on some possibilities with this. If we think about meeting prescriptive codes, working with somewhere between 30 and 40% of window to wall ratio. And what we've prepared is a couple of radiance images to show the differences between meeting the prescriptive code and meeting the performance code in a different construct using these materials. So here's an average, here's just an average elevation showing a variation of about 30 to 40% of punched opening windows and then solid opaque construction. And the option would be an all glass facade using the high performance aerogel Solera glass on the high bay and the low bay then using a ribbon of good performance vision glass and a solar shelf above it on the exterior. And if we look at them from a daylighting perspective, the first option, this is a deep floor plate office area on the inside and a false color rendering of what the actual daylight would be. This is a west-facing facade. And you can see, you can hardly even tell what's going on in that space because there is no daylighting factor to this at all. This is not a daylit space, even though it's got the prescribed number of windows in the space. And if you look at it from above, you can also see that there's no projection of light getting beyond the direct impinging area of the windows itself. If you take the same space and use the all-glass facade, same elevation, same day of the year, you've got a beautifully daylit interior space, both from looking at it at this standpoint as well as from above. You've got perfect light delivery through most of that space, and you would not need to use artificial lighting in the space during the daylit hours. And the nice thing about this is that the cost delta between this construct and the window to solid construct is quite small. So if there's value in the daylighting component, it's got an extreme amount of value to deliver the project. And the insulation performance between this wall construct and this wall construct are the same. So there's no difference in the thermal conductivity of the entire assembly. So this is the beauty of what this product does, is it allows you to tune light and then tune the insulation value. And you can do so for different elevations and different buildings within a very wide range. So it's a real design tool to use if you really want to practice daylighting and meet the energy requirements of buildings that you're working on today. And literally what it allows you to do in reality is to pull all of these things back together again and be able to design with all of these criteria met in a very, very creative and interesting way. And I don't know how I'm doing on time, but I put a lot of slides in here, and I'll just show you this. This is not a new technology. We've completed just under 1,600 projects and about 140,000 square meters of material at various locations in North America. We've got quite a number of installations in Norway at this time, some in the UK, and we're building our sales distribution system here, as well as I said earlier, installing fabrication in Northern Europe during this year. This is a beautiful daylight example here. This is how to get this done very quickly. And that's the end of my presentation. This is available. This is represented here locally out of Rotterdam with Herman's Technique Energy. And I'd be happy to take any questions and comments. Good. Okay. Thanks.